formula sheet, and you can use those on any problem. They're going to work. But a lot of times when I give you just a table of data, the formula is almost making it more complicated. Okay, these are our basic probabilities, like the first section, before we even got to all the formulas, because we didn't need the formula to calculate this. If we have the original data, we can find it ourselves. So I have the hours, watching TV, and the number of students that said they watched each amount. Okay, so let's add up our total number of students. We have 13 total students. So the probability a student is not watching television. So if they don't watch television, how many hours is that? 0. So the number of students that said that would be 2 out of our total number of students, so 13. On these probabilities, you can give me a fraction as long as it's in lowest terms, or just the decimal, 4 decimal places. Part B. What percentage of the class is watching at most 2 hours of television? So we still just have 13 students. At most 2. That means it could be 0, 1, or 2 hours of television. So how many students does that apply to? 7 out of 13, so you get 0.5385. What's the probability the student is watching at least 4? So what does that mean? 4 and higher. So 4, 5, and 6. So that would be 6 out of the 13 total students, or 0.4615. Alright, so we didn't have to go to the table or to the formula sheet and find any special formulas for this. If I have the original data, a lot of times we can just look at it and figure it out. Alright, let's look at the next one. So we have 3 different kinds of candies in here. There's 25 each of dark, milk, and semi-sweet. So part A, if a chocolate is selected at random, what's the probability that it is milk chocolate? So how many milk chocolates do we have?
25.
Out of how many total pieces of chocolate?
75.
So you get 1/3 or 0.3 repeating. Okay, B, if one chocolate is selected at random, what's the probability that it is milk or dark? So you could use the formula sheet and say, okay, probability of milk or dark. So that's the probability of milk plus the probability of dark minus the probability of being both. Or we can just look at it and say, okay, how many pieces of candy in the bowl are either milk chocolate or dark chocolate? 50, because there's 25 milk and 25 dark. So that's 50 out of 75, which gives you 0.6 repeating. Yes, ma'am?
So on that one, I used a formula, but I didn't subtract anything.
Right, because, so if you realize that these are mutually exclusive, then you would just use the easy formula. If you didn't catch that right there, then when you went to do the and, are there any pieces of chocolate that are both flavors? No. So then you would have the 25 out of 75 plus 25 out of 75 minus 0, and you get the same thing. Part C. If one chocolate is selected at random, what's the probability that it is milk and dark? So I'm going to take one piece of candy, and I want it to be both flavors. 0. There are no chocolates that are 2 flavors. That makes sense to everybody?
So what if you don't catch that and you put the numbers in the formula?
So probability of milk and dark is the probability of milk times the probability of dark given that it is milk, if you use your multiplication formula. So the probability of being a milk chocolate is 25 out of 75. If you already know that it is milk chocolate, what's the probability that it is also dark? 0, and so you get the same thing. So the formulas, they're not going to give you a different answer. You'll get the same thing. It's just 2 ways of thinking about it. All right. Next question. Let's talk about rolling a dice. So what is the probability that that number is a 3? So how many possible outcomes are there when you roll a dice?
6.
And how many of them are 3s?
1.
So So 1 out of 6, which is 0.1667. Probability of being odd. How many odd numbers?
3.
Out of how many total?
6.
So you get 0.5. Less than 5. How many options are smaller than 5? 4, because you can have 1, 2, 3, or 4. Out of 6, so 0.6667. A number no greater than 3. So what could it be?
1, 2, 3.
So 3 out of 6 is 0.5. Alright, on a problem like that, please make sure you're showing your work so you show your original fraction, not just your decimal. That's kind of in general. That way if you make a mistake plugging something in your calculator, I can give you the points for how you set it up and not take off everything. Okay, so try to show me some work on these problems if you can. Alright. Now, this table kind of gave some people some trouble. So you're probably going to have something like this on your quiz where we have a table, we have to read, but I'm going to ask all kinds of different things here. So when you have a condition, there are two ways to think about this. There's a formula, and we also just talked about it, how to work through it. You get the same answer. Okay, it's set up the same way, it's just a matter of how your mind wraps around it. When I say the probability of yes, given senior, the senior is my denominator. And that is all I'm looking at in this table. So how many seniors do we have?
67.
And then only looking at those seniors, how many said yes?
17.
So you get 0.2537.
Yep.
So what you need to remember, the conditional probabilities, it's not that it's hard, but you have to remember what goes where. Your condition is the denominator. So no given freshman. That means the only thing I'm going to look at here are the freshmen. How many freshmen are there? And how many of those said no? So 15 out of 50, which is 0.3. You guys see where I'm getting these? Is this helping at all, going over this stuff? So, the probability of yes, knowing the student is not a senior. So I've already given you the given, not a senior. So if you are not a senior, that means you could be a junior, a sophomore, or a freshman. So for my denominator, I add all of those up, and what do we get? And then, from that, the top is my yeses. So that's 100 out of 183. D. Probability of junior given no. So my given is my denominator. That's all I'm looking at in my table. So how many said no? Out of those, I want only the juniors. So that's 38 out of 133. So that's 0.2857. Yes, ma'am.
I know it does say like juniors given no, but like how would you know it's not yes just because it's given that it's no?
Yes. So, yeah, you want to try and answer that, yes? So when you have a given, that means I've already been told the answer is no. So I already know that for sure, so I don't even have to look at the guesses because I already had that information that told me it was a no answer. Alright. E, the probability of a sophomore student given the answer was yes. So my given was yes, so we only look at our yeses. So if you add all those yeses up, we have 117. And out of those, the sophomores, there are 40. So 40 out of 117 turns out to be 0.3419. understand the conditional probability. What if I had just said on this, so I might put, some conditionals and some not conditionals in the same problem. What if I just asked for the probability of a junior? What would you have to do then?
The junior divided by the student body.
Yeah, you would just have your juniors, which would be 63 out of everybody, which is what?
250.
So if I don't give you a condition, that's when it's out of everybody. Okay. If I had asked for the probability of junior and no. Okay, you can use a formula from this, but could I just look at the table and find junior and no?
No. Or, yeah.
Yeah, I can look and see how many students are juniors and said no. So then that would be 38. Did I give you a condition there? So it's still out of everybody. Okay, do you guys see the difference when it's out of everybody and when it's not? It's when you have that condition or that vertical bar, that given piece, that you are no longer looking at everything, just that part. If I don't give you that given, then you are out of the entire group.
And if it was an or two, you would still do that, but then add them together.
So if I said the probability of junior or no. Okay, there's no condition, so it's still out of everybody. You can use a formula, so you could use your or formula. Oops, that's not what I meant to do. Or we could just look at our table and say, okay, if they're a junior or they said no, then I need to look at all these people. So I would add up everything highlighted green out of my total. Does that make sense? Any other questions there? Moving on. Alright, so here is where we are really getting into the formulas. And my suggestion, if you don't know what else to do, look at the stuff you have and look for a formula that involves that. Okay? We have 2 formulas for and, 2 formulas for or, but the only time they have a special condition. You have to know they are mutually exclusive to use the first or formula. You have to know they're independent to use the first and formula. So I didn't say anything about mutually exclusive or independent, so you're using the general formulas here. So the probability of A or B, if I write out my formula, that's probability of A plus probability of B minus probability of A and B. So plug in. Please, on your quiz, show me some work here. Don't just put everything in your calculator and write down your final answer. I need to have some idea of how you got that answer. So we get 0.6. Okay, we didn't have to do any manipulating there. It was just a straight plugging in our formula. Number 6. I'm still talk about all the same pieces. So we're still talking about the same formula. Can I not copy it down again for the sake of time? So the probability of A or B is 0.9. Probability of A is 0.4. I do not know the probability of B. Minus probability of A and B is 0.1. So if you subtract over that 0.3, probability of B is 0.6. All right. 7. I gave you the conditional. We need to find probability of B and A. So we can use our general multiplication formula that says that's the probability of B times the probability of A given B. We don't know the probability of A and B. Probability of B is 0.8 times 0.5, and we get 0.4. So you use the, alright. So this one that she used, if you guys have your formula sheet handy. So I was using the Andy Moore formulas, but right, like the fourth bullet down, you have the conditional probability rule that says probability of A given B is probability of A and B divided by the probability of B. So probability of A and B is the same as probability of B and A. The order doesn't matter there. So then we can plug in, this is 0.5 equals probability of A and B divided by 0.8, and then multiply over your 0.8, and you get the same thing. So sometimes there's more than one way to set it up. That's why I encourage you to show me how you are doing it. Okay. Number 8. We talked about complements, and I told you there are two notations for a complement. On your formula sheet, it uses that little C up in the corner, but the other option I told you was a line over the top. So that just means not A and B. So to find the probability of A and B, anytime you want the complement, you just do 1 minus probability you have, so we get 0.3. So the probability of A, we need a formula. I have the or, I have the and, so I'm going to say probability of A or B equals probability of A plus probability of B minus probability of A and B. So if we plug in A or B is 1, probability of A we are trying to find, probability of B was 0.6, and we already found probability of A and B in part A was 0.3. So if you subtract over your 0.3, probability of A is 0.7. Probability of A given B, so again, you have two options. You can use that conditional formula, or you can use the multiplication formula. It doesn't matter, which one do you guys want me to do?
Multiplication.
Okay, so that says probability of A and B equals, you have to do the probability of the condition first. So probability of B times probability of A given B. So A and B we found to be 0.3. Probability of B was 0.6 times probability of A given B. So divide over your 0.6 and you get 0.5. Make sense? Okay. Moving on. So you have to know the definition or the difference between mutually exclusive and independent. Mutually exclusive is telling me that there is no overlap, that both things cannot occur. Independent is knowing one doesn't change the other. Okay, if I have 5 coins are tossed, the first outcome, no more than 1 head is observed. So that means that I could have 0 heads or I could have 1 head. Second outcome is 2 heads. This one is 3 or more, so you could have 3, 4, or 5. Is there any overlap there?
Yes.
This is 0 to 1, this is 2, this is 3, 4, or 5. So there's no overlap, so that's mutually exclusive.
I thought we put them all together.
Those are the 3 separate categories that I'm going to provide. So if I had each of you flip 5 coins, and I said, okay, everybody that got no more than 1 head, go stand over there. Everybody that got 2 heads, go stand back there. Everybody got 3 or more, come stand up here. Would any of you not have a place to go or be called to 2 different places at once? No, it'll only be 1 place where you would go. So they're mutually exclusive. Okay, if I tried to separate our class and I said, okay, if you're female, go here. If you're male, go there. If you're older than 16, go here. Would there be a problem? Yes, because you could fit into 2 groups at once, so you wouldn't know where to go. So this is not mutually exclusive. Okay, 2 dice are rolled. So the number of dots showing are both odds. So that means you could have like a 1 and a 1, a 3 and a 1, a 5 and a 1. You guys get the idea, right? 2 odd numbers. 2 even numbers. a total of 7. When you roll a dice, what kinds of things add up to 7?
3, 4,
4.
5, and 2.
Are any of those both even or both odd? No. So we still don't have any overlap. Total of 11. What would add up to 11?
6 and 5.
Okay. Do those also add up to 7? No. Are they both even or both odd? No. So this is mutually exclusive. You can't give me a combination that fit into 2 groups. Those groups are completely separate. Alright, independent, dependent. So rolling a dice and observing a 2 on one dice and a 3 on the other. So if each of us, if AJ rolls 1 and I roll 1, if I get a 2, does that make him more likely to get a 3? No, they have nothing to do with each other, so that's independent. Okay, raining today and passing today's test. Is that going to make a difference? No, so those would be independent. Raining today and playing golf today. Yes, because if it's raining, does it change the probability that you play golf? Absolutely. So those are not independent, they're dependent. Alright, number 11. If they are independent, look at your formula sheet. When we are talking about independent, you have a multiplication rule for independent events. So the probability of A and B, because I know they are independent, that's just probability of A times probability of B. So 0.5 times 0.8 gives me 0.3. All right. Number 12. We are still using formulas here, just practicing with our formulas. I have A and B separately. So probability of A given B. So if you want to use that multiplication formula, if you want A given B, which probability do I have to multiply by first? B. I encourage you guys to write out the formula on this one because that's the one thing that I was seeing problems with when answering questions on this. People were multiplying by the probability of A here. So make sure you write out your formula. So 0.12 equals 0.4 times probability of A given B. So divide by 0.4 and you get 0.3. Probability of B given A, so the first one you multiply by has to be your condition. So that'd be probability of A times probability of B given A. So A and B is 0.12, probability of A is 0.3 times probability of B given A. So you divide by your 0.3 and you get 0.4. Alright, are they independent? If they are independent, they don't change one another. So the probability of A would have to be the same as the probability of A if B has already happened. Or vice versa. The probability of B would have to be the same as the probability of B given that A has already happened. Is that true? Yeah, probability of A and probability of A given B. Probability of B, probability of B given A. Those are the same, so they are independent. If they are mutually exclusive, that means the probability of A and B has to equal what? 0. Does it?
No.
No, so they are not mutually exclusive. So make sure you know what independent and mutually exclusive mean. All right. Number 13. Okay, I am telling you right now that they are mutually exclusive. So let's jump to part C. If they're mutually exclusive, what's the probability of A and B?
0.
All right. Probability of not A, how do I find that?
Probability.
You get 0.6. If they are mutually exclusive, that's the same thing as saying disjoint. If you look at your formula sheet, then the probability of A and B is just probability of A plus probability of B. And you get 0.9. So far, so good? I worked out problem 14, or I set that up for you yesterday, didn't I? So I'm not going to go over that one right now. 15. according to the CDC, 77% of children aged 19 to 35 months receive all recommended vaccines. If 3 children are randomly selected, are these 3 children like from the same family or anything like that?
No.
Just 3 random children in the U.S. So would those be independent? Yes. So I want the probability that all 3 have been vaccinated. So vaccinated and vaccinated and vaccinated. So all you have to do is multiply those probabilities. So 0.77 times 0.77 times 0.77. Or you could just do 0.77 to the third and you get 0.4565. All right. When I say the sample space, you are telling me what it could be. So a sum of 8. So if Sarah and I each have a dice and we want them to add up to 8, what are my combinations?
1 and 4, 6 and 2, 5 and 3.
Okay. Is 2 and 6 different than 6 and 2 here?
Yes.
Yes, if I roll a 2 and she gets a 6, that's different than her getting the 2 and me getting the 6. So we have to list both. 3 and 5, 5 and 3.
What's an example where you wouldn't have to?
If I just said, like, so then you wouldn't need both. I'm struggling to come up with an example of when the order would matter. You got one?
Would it be like the example we did on one page where it's like he has to pick who's going to?
Yes, yes. Let's say I just wanted to pick 2 volunteers to come up to the board. If picking you and Joshua, is that different than picking Joshua and you? If you're both coming up and working a problem together? No. Now, if I were going to have one person do the first problem and one person do the second problem, then does the order matter? Yes. Thank you. I don't know why I was struggling there for a second. All right, C is doubles. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Are they mutually exclusive? No. The reason being 4, 4 is in both sets, so not mutually exclusive. Probability of A or C, if you want to use a formula, that's probability of A plus probability of C minus probability of A or C. Sorry, A and C. All right, we did a dice example in class, and we talked about how many total combinations there were. If there's 6 options for the first dice and 6 for the second, how many do we have altogether? 36 combinations. So A, there were 1, 2, 3, 4, 5 options. C, there are 1, 2, 3, 4, 5, 6. Minus, have we double counted anybody? Yeah, I've double counted 1 out of those. So you get 10 out of 36 or 0.2778.
Wait, how do you get that over number 36?
Well, I was kind of referencing the example we've done before, but there's 6 options for the first dice and 6 for the second, and 6 times 6 equals 36. If I put one on the quiz like this, which is very likely, I probably wouldn't necessarily give you one where you had to come up with that 36 on your own. So I might say, I have the numbers 1 through 10, and event A is an odd number, and event B is a number less than 3. And so you would know that there were only 10 possibilities. So I would give you something that you wouldn't necessarily have to count up how many options there were.
If we were flipping a coin, we could take, and say we were flipping it 5 times, we could take 2 to the 5th power.
0.5 to the 5th, yes.
0.5.
Yes. All right, everybody good with me there? So that's the first handout, which should be absolutely perfect now and make complete sense.
Do you have number 16?
Hmm.
It is.
Oh yeah, sorry, I got ahead of myself. All right, let's talk about this one. So probability of 2 defective parts. That means we're selecting 2, so the probability first is defective and the second one being defective. So what is the probability of the first part being defective? 3 out of 22. 3 out of the 25 total. Without replacement. That means I didn't put that part back in the box. I'm set it over here on my table. I'm going to take another one out. So how many defectives are in that box now? 2 out of my 24. And that gives you what, 0.01? Okay. The probability of one being defective. Okay. I'm going to take one out, set it over here, then take another one out. So it could be that the first one is defective and the second one is not. Or the first one could not be and the second one is. So the first one being defective would be, and the second one not defective, or, so plus, the first one not being defective, 22 out of 25, and the second one being defective, 3 out of 24. And so we get 0.22?
Yep.
Okay, probability of none defective. So that's non-defective and non-defective. So the first one, there are 24 non-defective out of the 22 out of the 25 total. And if I took out one that's good, now there's only 21 out of the 24. And so that gives me 0.77. What do these add up to, guys? 100. Because 2 being good, or 2 being bad, 1 being bad, and none being bad, that's every combination. So you could have even done 1 minus the other 2 that you had calculated there. Okay, I know we are not probably going to have time to get through all of this. So let's kind of talk about as much as we can before the end of class. This table, let's run through it quickly. We want a male and over the age of 59. So you can use a formula, but you don't have to, because can you just look at this table and find out how many males are over 59? Yes. All you have to do is add those 3 people together, which is 1196, out of, there's no condition, so it's out of everybody. So 10,691. And you guys can divide this later, right, since I'm short on time? Okay, B. There's still no condition, so it's still out of everybody. I want female or under 30. So I have to add up all my females or the people under 30. So again, you can set up a whole formula, but you don't have to, because you can just look at your table and see which numbers we need to add together. So if I do that, add up all those people, you should get what? I set mine up differently on my key, so.
1,373.
That's all the male.
6,727.
Yeah. If you add up all those and divide them. I think your number was just these males.
We did the
and
formula there, we had to subtract.
Yeah, you would have done the probability of being female, so you would have done all your females, plus probability of being under 30, so you would have added up all those, and you'd have to subtract off those 2 that you double counted. Okay, C. Now I gave you a given, so it is no longer out of everybody. We are between 20 and 49. So I am only looking at these 6 numbers. So your denominator, you add those 6, and you get 5,294. Then you only want the females from that, which should be 2,636. D. My given is the driver is female. So that's my denominator, just these females. So you add up all your females, and that's 5,354. Then you are only looking at the ones between 20 and 49. So then you add up those 3, and you get the 2636. Okay, so you see the difference between C and D. There's a different probability based off what I knew to start with. Alright, so I'm going to leave it to you guys to finish those if you had to correct any of them, but I've got it set up for you. Number 2. Do we need to go through this one? Okay. We'll come back to it if we have time. What about 3?
Can we just go over
Okay, so the probability of B given A. They are independent. That means the conditional probability has to be the same as the original probability, because knowing one thing doesn't change the other. So it's just a 0.1. Because they're independent, the and, all you have to do is multiply your probabilities. So the probability of A is 0.8. What's the probability of not B? 1 minus 0.1, so you get your 0.9. Not A or B, so that'd be the probability of not A plus probability of B minus probability of not A and B. Is everybody with me here? Sarah, are you with me? Hit her, please. Okay, probability of not A. So if A is 0.8, the probability of not A would be 0.2. Probability of B would be 0.1. How would I find the probability of not A and B? Multiply. So you just have to do your 0.2 times 0.1. And then you should get your final answer there.
For B, how did you get 0.9?
It was not B, so I did 1 minus the probability of B. So anytime I want to complement, it's just 1 minus. All right, number 4, this table. Do we need to look at it? Make sure you are correcting these as we go through them if you have any mistakes. I'm going to be looking at them tomorrow, and everything better be perfect. All right, we'll come back to it if we have time. Number 5, do we need this one? Yep. So let's just run through. I might as well go through all of them while we're here. Part A is seedless. So you have 10% are pink seedless and 20% are white seedless. So 0.1 plus 0.2 is 0.3. 30% are seedless. Pink or seedless. So that means you would have the probability of pink plus the probability of seedless minus the overlap if you were doing the formula, right? Probability of being pink. So we have 10% and 30%. So the total probability of being pink is 0.4 plus the probability of seedless we just found was 0.3 minus, we have double counted this pink seedless, and so we should get 0.6. Everybody with me there? All right, C and D, we have conditional, so it is no longer out of everything.
When I did that one, number B, I just added 0.1 plus 0.2 plus 0.3.
You could have, because I gave you the numbers, you didn't have to do a formula. You could have just added up everything that was either pink or it was seedless. So it's basically everything except those that are white with seed. So probably 3 different ways you could have done that one. So on C, given it is seedless, so my denominator is the seedless. That's all I'm looking at. So how many are seedless? 0.3. Now I'm still only looking at those 2 numbers. How many of them were pink? So that's 0.3 repeating. D, seedless given it is pink. So my denominator is the pink. So this is pink and this is pink. So how many are pink? Only looking at those 2 pinks, how many are seedless? You get 0.25. Okay. What do we really need to go through before we run out of time here?
Maybe 1 like 11.
Okay, so 10 and 11. All right, problem 10. Both are heads. So that's the probability of the heads on the first and heads on the second. Are these independent? If you flip one coin, does that change what happens on the next? No. So we can just multiply them. So what's the probability of getting a heads on the first? 0.6. What's the probability of a heads on the second?
0.5.
So we get 0.3. Because it was balanced, it's a 50-50 for the second coin. Alright, probability of exactly one head. So that could mean there's heads on the first and tails on the second, or tails on the first and heads on the second. So heads on the first, there's a 60% chance. What about tails on the first? 4 means plus. Tails on the first is heads on the first is 0.5. So if you multiply, you get 0.3 plus 0.2, so 0.5.
How did you get the 0.1 then?
There's a 60% chance it's heads, so tails would be the complement, 1 minus that. Alright, if neither one is heads, what does that mean? They're both tails. Okay, what's the probability of tails on the first? 0.4. What's the probability of tails on the second? 0.5. So you multiply those and you get 0.2. Okay, you notice what do these three things add up to? 1, because it's every combination. 2 heads, a heads and a tails, or 2 tails. Alright, D, it's a conditional. So your condition is the denominator. Coin A is heads. What is the probability that coin A is heads? Okay, here's where it's tricky. Both show heads. Okay, if coin A is a heads, then for both of them to be heads, that's heads and heads, which we've already calculated is 0.3. So you divide those and you get 0.5. E. My condition is coin B is a head. So what's the probability that coin B is heads? Alright, then what's the probability that they both show heads? So you get 0.6. Is this making sense to everybody? Is this worth my time to go through these reviews? Okay. Last one. Exactly one head shows. So what's the probability of exactly one? 0.5. We found that in part B. Now this is the trickiest problem up here. I want heads on coin A. There's only one heads total. So if coin A is a heads, that means coin B is tails. So that was what we found right here. Heads on A, tails on B. So that was 0.3. So that comes out to be 0.6. So that last one, that last conditional there, did require a little more thought than the others. All right, number 11. I really like this question. We've had several of these where we just did kind of the same thing with the coins, you know, 1 head, 2 heads, no heads. We did one like it with, what were we talking? 2 defective, 1 defective, none defective. Now I'm doing 2 damage free, 1 damage free, none damage free. So you might expect me to put something like this on here because we've done it a few different times now. So we have 15 tires. 5 have internal damage and 10 are damage free. We are purchasing 2. So the probability that both are damage free, that means I want 2 good tires. What's the probability that the first tire is good? Where I wrote 13, 10, there's 10 good ones. And if you've already taken 1 good tire, what's the probability the second one is good? Okay, and so you get 0.4286. What's the probability that exactly 1 is damage free? So what do I have to find?
Good and bad, bad and good.
Okay, so the first one being good, there are 10 out of 15. And then second one being bad, there would be
5 out of 15.
or, so plus, the first one being bad, so that would be,
5 out of 15.
and the second one being good. So if we multiply those, we get 0.4762. What's one way you could get this last one? Yeah, these should all add up to 1, right? So you could do 1 minus the other 2. or the probability that at least one is damage free. Okay, so we've got probability of both, we've got probability of one, so you can recalculate it all, or just add, and you get 0.9048. So if I wanted the probability of them both being good, or both being bad, what would you do?
Subtract from one.
Subtract from one. Alright. Anything else? We've got like a minute.
Wait, what's the actual formula on that one?
Well, at least one being damage free, you could do a 1 minus probability that they're both bad. Or you could